On December 2nd, 2023, at 2:37 p.m. Manila time, something catastrophic happened beneath the ocean floor off Mindanao that nobody predicted. A 7.6 magnitude earthquake ripped through shallow waters, and what followed shocked seismologists worldwide. But there's one critical detail almost every news channel got wrong about what actually triggered it. Part 1. The Forgotten Earthquake. Most people watched it happen on their phones, felt it through their windows, or scrolled past it on social media. But within 27 days of that December 2nd main shock, the Philippine Seismic Network recorded over 8,400 aftershocks. 8,400. Think about that number. That's not a single earthquake story. That's a geological crisis unfolding in real time. The epicenter was located just 19 kilometers east of Gamut and 29 kilometers northeast of Hinatuan in Surigao del Sur province. On the surface, it looked like just another Pacific earthquake, another tremor off the coast, another news cycle. But beneath the ocean, something far more complex was occurring that contradicted everything scientists thought they understood about how Mindanao's earthquakes should work. The December 4th aftershock measured 6.9 magnitude on its own, powerful enough to be catastrophic independently. Yet it wasn't treated as a major earthquake. It was just classified as an aftershock, almost like a footnote in the story. This is precisely what mainstream coverage missed. The interaction between these seismic events was revealing something unprecedented about Mindanao's underlying geological structure. Scientists initially reported this as a magnitude 7.4 event, then revised it upward to 7.6. The shaking lasted more than 30 seconds in the epicentral area, an eternity when the ground beneath you is moving. At Malapatan in Sarangani, the earthquake intensity reached 8 on the 5-Olg scale, which means very destructive. Homes collapsed. Bridges fractured. Ground liquefaction was recorded at 23 separate sites across Surigao del Sur, primarily in low-lying coastal areas where soils literally turned from solid to liquid from the violent cyclic loading. But here's what makes this different from other Mindanao earthquakes. The mechanism was wrong. If you're amazed by our ancestor story, the Mindanao earthquake mystery, what mainstream media missed? Help us hit our 500-like goal, drop a comment about your favorite fact, and subscribe to join the Histo PH family. Part 2. The wrong mechanism. This is where news failed. Every textbook, every seismology course, every USGS educational material tells the same story about Mindanao earthquakes. The Philippine Sea Plate, carrying ancient oceanic crust from millions of years ago, collides with the Sunda Plate at approximately 103 millimeters per year. That's not fast. That's extremely fast for a subduction zone. When you have two plates grinding together at that speed, you get predictable patterns. Except this earthquake wasn't predictable. The December 2023 main shock ruptured along a thrust mechanism, plates pushing one atop another. This is standard for subduction zones. You have a descending slab of oceanic plate, and it generates thrust-faulting earthquakes as it subducts beneath the continental margin. Scientists have been mapping this pattern since the 1920s. Mindanao's strongest earthquakes from 1920 onwards, magnitudes ranging from 7.1 to 8.3, all followed this same thrust-faulting pattern. But then the 6.8 earthquake followed with a completely different focal mechanism. It operated on a normal fault, the opposite of thrust. Plates pulling apart instead of pushing together. In the same region, days apart. This shouldn't happen. This violates the standard model. And when geologists from the University of the Philippines Structural Geology and Tectonics Laboratory investigated why, they found something extraordinary hidden in the subducting slab, an extinct oceanic fracture zone. Part 3. The hidden fracture zone, what nobody talked about. Imagine the Philippine sea plate as a conveyor belt of oceanic crust carrying the geological history of millions of years. When that plate was forming on mid-ocean ridges decades ago, it developed fracture zones, ancient breaks in the seafloor created by transform faults. These fractures are like scars in the oceanic crust, now extinct, but still present in the rocks as they descend into the subduction zone. As this ancient scarred oceanic plate moves westward toward Mindanao at 103 millimeters per year, it carries these fractures deep into the earth. The Philippine Trench, which reaches depths of over 10 kilometers at the surface but extends far deeper into the planet, is where this collision occurs. What researchers discovered was that one of these extinct fracture zones, now active in a new way because it's being stressed by subduction, was lying directly in the path of stress accumulation from the main shock. The magnitude 7.4 or 7.6 thrust earthquake created what's called Coulomb stress change. It redistributed pressure across the subducting slab. Think of it like pushing on a wall covered in weak spots. When you apply force to one section, nearby weak areas suddenly experience different stress. If you apply enough pressure, those weak areas can rupture too. The extinct fracture zone in the subducting Philippine sea plate was exactly that kind of weak spot. The main shock triggered stress transfer to this fracture zone, which then ruptured with a normal fault mechanism just days later. This was the smoking gun that mainstream coverage completely missed. The December 2023 Mindanao earthquake sequence wasn't just one tectonic event. It was a cascade of events along different fault types in the same subducting plate, something that violates conventional seismic hazard models and suggests Mindanao's earthquake potential is far more complex than previously understood. Part 4. Why the Philippine Trench is the deadliest seismic zone. Nobody talks about. The Philippine Trench stretches along the entire eastern edge of the Philippines, from Bicol in the north all the way down the full length of the Visayas and Mindanao. It's not one continuous structure. It's a 1,300-kilometer zone of relentless plate collision. The convergence rate of 103 millimeters per year is considered fast for a subduction zone. To put this in perspective, most subduction zones operate at 30 to 60 millimeters per year. The Philippine Trench is nearly twice as active as average. This speed generates enormous stress accumulation and enormous earthquakes. Historical records dating back to the 1800s reveal a pattern that should terrify everyone in that region. An 1879 earthquake along the Surigao segment, the exact area where December 2023 struck, reached magnitude 7.4. An 1891 event hit magnitude 7.2. In 1893, another shock measured 7.3. These weren't isolated events. They were systematic stress release along a zone that was continuously accumulating plate collision energy. The strongest recorded earthquake from the Philippine Trench was an 8.2 magnitude in 1924. In 1975, a magnitude 7.6 normal faulting intraslab earthquake ruptured there. In 2012, another 7.6 magnitude reverse faulting shock struck. The pattern is unmistakable. This is the most seismically productive zone in the Philippines, yet it's rarely featured in earthquake education or media discussions of Pacific seismic hazards. When the 2004 Indian Ocean earthquake and tsunami killed over 200,000 people, the world learned about subduction zones. When Japan's 2011 earthquake devastated Honshu, subduction zones became household words, but the Philippine Trench, which produces earthquakes just as large and affects millions of people, remains obscure. Part 5. The Stress Transfer Mystery. When researchers used Coulomb stress modeling after the December 2023 sequence, they made a disturbing discovery. The main shock didn't just trigger a single aftershock. It created cascading stress changes across multiple fault segments in the subducting slab. This is called stress transfer, and it's one of the most dangerous earthquake dynamics. One rupture can load stress onto adjacent faults, increasing the probability of subsequent earthquakes. The 7.4 main shock generated thrust faulting, which created stress on the nearby normal fault, the extinct fracture zone, which ruptured as a 6.8 magnitude event. But it didn't stop there. Within 2 months, earthquakes began occurring in what scientists describe as surprising locations. The February 2024 earthquake sequence that followed struck in areas that shouldn't have been affected by the December rupture's stress field, according to standard models. This suggests that either the stress transfer was larger than expected, or the underlying fault structure is more complex than seismic networks had mapped. Both possibilities have serious implications. If stress transfer is larger than modeled, then earthquake-triggering cascades could be more dangerous than current hazard assessments account for. If the fault structure is more complex, then seismic hazard maps may be incomplete. Part 6. The Geological Setting. Nobody explains properly Mindanao sits at the collision point of 3 major structures. The Philippine Sea Plate subducts to the east along the Philippine Trench. The Sunda Plate subducts to the west along the Cotabato Trench. And between these two opposite dipping subduction zones runs the Philippine Fault, a massive left lateral strike-slip fault that cuts Mindanao north to south like a geological knife. This creates what geologists call shear partitioning. The oblique convergence between the Pacific Plate and the overriding Philippine Mobile Belt isn't straight on, it's at an angle. That angular collision splits into 2 components: vertical, subduction along trenches, and horizontal, strike-slip motion along the Philippine Fault. No other region on Earth has this exact configuration of dual opposite-facing subduction zones with a major transform fault running between them. The Philippine Fault itself generates earthquakes of magnitude 7.0 to 7.3. A 1968 earthquake along the central Compostela Valley segment measured approximately 7.3 magnitude and created surface ruptures with visible ground cracks. A pre-instrumental earthquake in the same segment, based on historical accounts, reached an estimated magnitude 7.5, the highest documented earthquake along that particular fault segment. Eastern Mindanao also has another major fault system: the East Compostela Valley segment, the West Compostela Valley segment, and the Central Compostela Valley segment. Each segment can rupture independently or partially rupture, creating complex earthquake sequences that don't always follow expected patterns. Part 7. Why 2023 was different. The December 2023 sequence was unique because it demonstrated that the Philippine Trench subduction zone might be more seismically active than historical records suggested. The rapid succession of magnitude 7+ level earthquakes within days, the unexpected normal faulting mechanism, and the extensive aftershock sequence, 8,403 recorded events in 27 days, with 425 aftershocks above magnitude 4.5 alone, recorded by the USGS, showed that stress accumulation in this region is far more complicated than simple plate collision. Most textbooks suggest that subduction zones accumulate stress over decades or centuries before releasing it in one major earthquake. The Mindanao data suggests something different. Rapid stress transfer, complex triggering mechanisms, and multi-fault rupturing can occur in ways that don't match predictive models. Within the 27-day period after the main shock, the average was 312 earthquakes per day. The seismic network was registering seismic events constantly. The largest aftershock, 6.9 magnitude on December 4th, was so powerful it would normally be considered an independent earthquake if it occurred anywhere else. But here, it was just classified as an aftershock, a footnote in a larger story. Part 8. The Liquefaction Discoveries. When the Philippine Institute of Volcanology and Seismology, PHIVOLS, and Department of Science and Technology, DOST, conducted post-earthquake surveys in early 2024, they identified ground liquefaction at 23 separate sites across Surigao del Sur. This is significant because liquefaction indicates soil failure, where solid ground temporarily behaves like liquid due to intense cyclic shaking. Liquefaction occurred primarily in low-lying, swampy coastal barangays, where soil composition is already saturated with groundwater. But the extent of liquefaction was unusual for a 7.6 magnitude earthquake. The prolonged shaking duration, over 30 seconds in the epicentral area, combined with the shallow depth, 40 kilometers, meant that seismic waves maintained high amplitude longer than they would have if the earthquake was deeper. What scientists observed in these liquefaction zones was subsidence, ground sinking, and lateral spreading, horizontal ground movement of up to several meters. In one location, the ground literally moved sideways by multiple meters. Structures built on these soils failed catastrophically. Underground utilities fractured. The liquefaction wasn't just a minor side effect, it was a major failure mode that destroyed entire neighborhoods. The fact that 23 separate liquefaction sites were documented means this wasn't localized damage. It was distributed ground failure across the region, suggesting that the earthquake's ground motion was intense and sustained across a wide geographic area. Part 9. What makes the Philippine Trench earthquake zone lethal? The Philippine Trench's deadliness comes from 4 factors that rarely occur together. First, speed. At 103 millimeters per year, the Philippine sea plate is subducting faster than almost anywhere else on the planet. Faster subduction means faster stress accumulation. shorter recurrence intervals between major earthquakes, and less time for society to prepare. Second, shallow depths. Unlike deep subduction zones, the Philippine Trench's earthquakes often occur at shallow depths, 30 to 60 kilometers. Shallow earthquakes cause stronger ground shaking at the surface because the seismic energy doesn't have as far to travel and dissipate. The 2023 main shock occurred at 40 kilometers depth, which is relatively shallow. Deeper subduction zones might dissipate more energy. Third, population proximity. Mindanao has over 28 million people. Davao City alone has over 1.6 million residents. These cities sit directly above or near the Philippine Trench subduction zone. Unlike Japan, which has extensive earthquake engineering standards nationwide, or Chile, which has strict building codes specifically for seismic resistance, many structures in Mindanao don't meet modern earthquake safety standards. A magnitude 8.0 earthquake under similar conditions could cause catastrophic casualties. Fourth, triggering complexity. The 2023 sequence revealed that earthquakes along the Philippine Trench can trigger subsequent earthquakes on different fault types through stress transfer. This means a single rupture can initiate a cascade of seismic events that continues for weeks or months. This is harder to prepare for than a single, isolated event. Part 10. The stress accumulation problem. Here's the reality that seismic hazard assessments struggle with. We don't have complete historical earthquake records for the Philippine Trench. Our detailed instrumental earthquake catalog only goes back to about 1900. Before that, we have written historical accounts and geological evidence from paleoseismology, but the record becomes increasingly incomplete. This means we don't actually know how many earthquakes occur in this region over long time scales. The 1897 earthquake, estimated magnitude 7.3, and 1924 earthquake, magnitude 8.2, are in our records, but there could have been other major events that weren't recorded in those pre-modern times. Without a complete historical record, we can't accurately calculate how much stress is accumulating. The 2023 sequence suggests that stress accumulation rates might be higher than previously thought, or that stress is being released through multiple smaller events rather than rare mega-earthquakes. Either interpretation has important implications for long-term seismic hazard.